Hello, this is Jack Jackson. Today we're going to be looking at systems of linear inequalities and applying those in some linear programming applications. So basically two topics here: graphing the systems of linear equalities, graphing the solution set, and then do some linear programming applications of this. So when we have a system of linear inequalities, the graph of the solution set, remember, if you have just one inequality in two variables, it's a region of a plane bounded by the graph of that equality. If you replace the less than or greater than or whatever with an equality, put that as your boundary curve, and then you get that divides the plane into two parts. Half of that will be in the set and the other half won't. So if our boundary curve is a linear equation, then of course the boundary is a line, and then the graph of the linear inequality will be a half plane. If it has or equal to is included in the inequality, if it's a less than or equal to or greater than or equal to, then you'll have a solid boundary line, or in general a solid boundary curve. Whereas if it's a strict inequality, a less than or greater than, then you'll have a dotted boundary curve. We've already seen examples of this. When we have a system of linear inequalities, they're joined by an implied logical operator and. Remember, and corresponds to intersection. So what we're looking at is the overlap of all of the solution sets. So we take these half planes, in the case of linear inequalities, and we see where they overlap for two of them, and see where that region overlaps again and again and again. And so the solution set is the intersection of all the solution sets. So to be in the solution set, all of the inequalities must be satisfied. Or to look at it the other way around, any point that violates any one of the conditions will not be in the solution set. So sometimes it's easier to think of this in terms of what's erased than it is in what's shaded. So let's look at an example. You should probably be able to do this now. We've already talked about graphing these inequalities. You just want the part where they all three overlap. So let's take a look at this. So we're graphing them one at a time here. X is greater than or equal to 0. You can think of it two ways. You can think of graphing x equals 0 here, which is the boundary line, which is included, and then we shade the ones that are to the right, because those are the ones where x is greater than 0. Or you can think of erasing the ones to the left. Next, we graph the ones where y is less than or equal to 5. We can shade the ones where y is less than or equal to 5. Of course, y equals 5 is this boundary line up here at the top. And we've shaded this region down here below. So this part over here is y equals less than 5, all this. And this is x greater than 0. Now, of course, so far when we're just looking at those two inequalities, we're looking at the solution set being this double shaded region down here, sort of to the right of x equals 0 and below y equals 5. So this part up here is already erased. Now we put our last one when y is greater than x. First of all, notice that this time when we graph the boundary line y equals x, it's a dotted line because y equals x is not included, but we shade up to that line. In this case, we want the y's greater than the x's, so it's above that line, so it's up here. Now if you look, this little triangular region is the part that's triple shaded. Again, probably what I would think of doing here is, instead of shading, think about erasing. Think about with a whole plane here. We first erase the x is less than 0, anything over here. Then erase anything above y equals 5 up here. And then we erase anything down here that is to the below the line y equals x. And what are you left with? You're left with, once you do all the erasing, the only thing that's left is this right here. And notice this is the solution set. A couple things. One thing that we do need to work out that's not illustrated well here is this intersection point right here is a solid dot because it is on this solid line, and this solid line segment are included, so they overlap at that solid dot. But things along this line, this edge, are actually erased. So that point at 5, 5 and this point at 0, 0 are actually erased. So they should probably look as little open circles. Dots showing that those points are not actually included. So in the end, we get this region of xy's that are here. So for example, the point 1, 3 right there is in the region, and so it should make all of these work. 1 is greater than 0, 3 is less than or equal to 5, and 3 is greater than 1. So that does work. 5, 5 does not work because 5 is not greater than 5. It satisfies these other two, but not that one. And so forth. If you pick a point out here like 4, 1, it should make at least one of these false. 4 greater than 0 works, 1 less than or equal to 5 works, but 1 greater than 4 is false, so that it makes this last one false. And so we get a region like that. Okay? Your turn. This one has 4 boundary curves, all of which are lines. Notice which ones should be dotted, which ones should be solid, and go ahead and work this out, and when you finish, come back and let's check your answer. Okay? X greater than or equal to 1. Here we go. Y less than negative 3x plus 2. And see, of course, if it extended that far, we would have 0, 2 there, and right 1 down 3. And so you can see right 1 down 3, and that gives you that line. It's dotted, and we're shading over here. How do we know it's this side we shade? Well, a couple different ways we can see that. Since we have it in the form y less than or greater than something, when we have y less than an expression, that means we're graphing below the line. Of course, you can also do it with the test point, test 0, 0, and it makes this true. So we shade this side of the line. So that means we're double shaded here. So at this point, actually, the way I think of it is more erasing. This part's already been erased, so it doesn't come into play. So really this line starts here and goes on out this way, making a ray, and we erase all this line up here and this part out here. Or we're thinking of the double shaded region here. Now let's add another one into it. Y greater than x minus 5. So here's y equals x minus 5 right here, and the dot, again, it's a dotted line because the or equal to is not included. And notice that line starts at 0, negative 5 here, and goes up right 1, up 1. And so you can see that, graphing that line here. Again, 0, 0 makes that true, so it's this side of the line that's shaded. So now we would erase down here. Now if you think about it, what's been erased? Well, all this has been erased. The only thing left at this point is this little triangular region. We still have one more to go, though. So the triangular region is triple shaded. What about the fourth condition? The fourth condition is y less than or equal to 2x minus 4. I think I wanted to change that. Let's see here. Let me go to the next slide. I think it is y is, let me fix this to be what I want it to be. Y less than or equal to 2x minus 4 is the region I want. So let me change that. Sorry about that. Less than or equal to. Now if you'd graphed y greater than or equal to 4, 2x minus 4, you would have been left with this little triangular region at the top. If I graph less than or equal to 2x minus 4, I get this region below that. So that's the one I want to graph. Let me fix that here. All these slides real fast. It's going to take me just a second to do this. Sorry about that. Now, if you graph the original one, of course, like I said, you'll end up with that triangular region. Okay, so let's go back to this slide here. Okay, as I said, if you graph y greater than that, you would have a dotted line going along right here, and you'd only be left with this triangle. In which case, this equation right here about y being greater than x minus 5 didn't really even matter, because it's just redundant information. But if I change it to this problem, then you get graphed what I have here, which is this little quadrilateral region right here, this region right here. So if we erase all this other stuff, then, and I zoom in a little bit, this is what the graph looks like. And this one's actually graphed right here. So we have a solid dot here where we have the two solid curves meeting. And any place we have a dotted curve meeting, whether it's meeting a solid curve or two dotted curves, that point is not included, so we graph it like this with an open dot at that. Now, this is a polygon, and so you want to be sure to identify the coordinates of those corners, the vertices. Now, I've also labeled the equation for the boundary curves. This is part of the line x equals 1. This is part of the line y equals 2x minus 4. This is part of the line y equals negative 3x plus 2. And this is part of the line y equals x minus 5. Notice this line doesn't really go on because we've erased the part outside of that. So even though you may have graphed it earlier, in the end you're going to erase some of it. Okay, what are these points of intersection? Well, these two here are going to be the easiest to get. When x is 1 and y is x minus 5, then we see y has to be negative 4. Just plug in x is 1 here and solve for y. Similarly, when x is 1 here, we plug in this formula up here, y equals 2x minus 4, to get y is negative 2. So that gives us the points 1, negative 4 down here, and 1, negative 2 here. Now what about these 2 points with the decimals? Those are a little bit harder, but not too hard at all. We just have to solve this system of equations, y equals 2x minus 4 and y equals negative 3x plus 2. Since they're both solved for y, let's just do it by substitution. We get 2x minus 4 equals negative 3x plus 2. Pretty easy to solve. Let's see, add 3x to both sides, that gives us 5x. Add 4 to both sides, we get 6. We get 6/5, which is 1.2 for x. Once you get 1.2, plug in either 1 to get y. So we plug in here. 2 times 1.2 is 2.4, minus 4 is negative 1.6. How about down here? We're setting these two equations equal, y equals x minus 5 and y equals negative 3x plus 2, solving that simultaneous system. Again, just substitute. We get x minus 5 equals negative 3x plus 2. Add 3x to both sides, you get 4x on the left. Add 5 to both sides, you get 7. So then divide by 4, you get 7/4, which is 1.75. Once you get 1.75, plug it in here and subtract 5 and get negative 3.25 for y. So easy enough to do that. Okay? And so there is our region. Now you may notice that this is what we would call a bounded region. A bounded region, you can draw a circle around the entire thing, and the entire graph is contained in the interior of some circle. Might be a big circle, but some circle. It's not, however, what we call closed, because it has these open edges on the edges here. So for it to be closed, you'd have to have it ought to all be around like this. It'd have to have a solid boundary all the way around to be closed. Alright, here's another one. You try this. When you finish, come back and let's test it. Check it out. Press pause now. Alright, this one is an unbounded region, and it's the triple shaded region right here. Let's see, this curve, let's see, if we graph, it is got closed boundaries on it all the way around, but we have y equals negative 4x plus 6. That's going to be this curve right here. So it goes up here, just off the screen it hits at 6, or right at the edge of the screen, 0, 6, and you go to the right one and down 4, right one, down 4, right one, down 4, and graph that. This one is and notice that that 0, 0 is included, so that's going to be on the other side. If we graph y is greater than or equal to x minus 3, that's going to cross here at 0, negative 3, and goes to right 1 and up 1, and so forth, and it graphs there. This is y equals 2x minus 3. It also goes through 0, 3, but when you go to the right 1, you go down 2, or left 1, up 2. Now, one way you can do this is just to graph all the lines and then look at the regions. You have 1, 2, 3, 4, 5, 6 regions. And you can do a test point in every region to see which ones are shaded. It's another way to do it. You could test 0, 0, and it makes them all true. Okay, 0 less than 6, work this out, 0 greater than -3, 0 greater than or equal to -3. So that one works for all. So that one's triple shaded, so this whole region is triple shaded. And if you do anything, any point out here, like 2, 0 might be a good test point in this region, 4, 0 might be a good one for this region, 0, -4 for here, -2, 0. If you check any of those points, and then maybe even one in this region, like 1, -3, all those points fail in one or more of these inequalities, so all those regions would be erased. Another way to look at it. You do need to be sure and get these intersection points. We kind of already sort of stumbled across this one at 0, -3, and then we need to kind of compute this one. That's when the let's see, the one with the positive slope, this one, y equals x minus 3, is solved simultaneously with the first one, -4x plus 6. So again, since they're solved for y, put them equal, the equal to's here, and so we get x minus 3 equals -4x plus 6. Add 4x to both sides, that's 5x. Subtract 6 from both sides, that's -9. So x equals -9, or x equals, I'm sorry, wait a minute, 5x -4x plus 6, 3x, x minus 3, okay, yeah, so you're adding 4x to both sides gets 5x, then you're going to add 3 to both sides to get 9, so x equals 9/5, which is positive 1.8, so that's correct. Then the next, once you find 1.8, you can plug in either one of these, say this one, just subtract 3 and get -1.2, and so that's that point there. So when you look at this, this is what it looks like when you erase everything that doesn't need to be there. It does have solid dots at the corners, solid dots, solid along the edges. This edge is a line segment, but this edge and this edge probably should have little arrows on the end, because this goes on forever. And so this is not a polygon, it's open-ended up here at the top. So this is an unbounded region. No matter how big we make a circle, we can't contain the whole thing. Alright, another one to practice. Try this one out. Press pause, come back when you get it done. Well, when it's all said and done, this is what it looks like. I've got the boundary curves, x equals 0, y equals 2x, y equals -4x plus 6, and y equals x minus 3 labeled. In this case, it's closed and bounded. The corners, the vertices of this quadrilateral, this polygon, are important for us. They're at 0, 0, the origin there, coming down, 0, -3, coming across here, 1.8, comma -1.2, and coming up here, 1, 2. Okay, so hopefully you found this region and labeled those coordinates of those vertices when you did this on your own. So notice that this region is closed and bounded. It's contained all inside a circle. You got solid boundaries all the way around, so the corners are included, the vertices are included, as well as all these points in between. Okay? In fact, this is a polygon plus its interior, a quadrilateral plus its interior. So let's take the same region, okay, and what we can do sometimes in what we call linear programming problems is we have a function of two variables, or a function where the input is an ordered pair and an output is a single number. Okay, so instead of saying f of parentheses x comma y parentheses parentheses, instead of putting two sets of parentheses, we sort of drop one and we just say, think of this as a function of two variables. So our input is actually an ordered pair and our output is a real number. Okay, and we want to find the largest and smallest values this one takes, but it is restricted to this domain. So if you just looked at this formula, you might say, well, x and y could be any real numbers. We get the whole plane for the domain. But let's say it is restricted to the things in this set up here, in this set that we have graphed. So there's only going to be inputs that are shaded here in red. Okay, and the outputs are going to be given by that function. So let's think about this a minute. Okay, graphically, really, this is kind of a 3D thing. It's like z equals 2x minus 3y plus 5, which is a plane. But we can kind of get a sort of a two-dimensional version of a graph called a contour graph, and this is what we're going to do next. So what values of the domain make f equal to 10? Okay, let's think about what that means. So we're going to place the 10 in place of the f. So that's over here on the left, we put 10. So now we're graphing 10 equals 2x minus 3y plus 5. But we're only going to graph, which is a line, right? But we're only going to graph the part of that line that stays inside the red here. So it'll have endpoints on some of these boundary curves, and in between it'll be a straight line going somewhere or another. See if you can graph that. Then repeat for a new value of f. Plug in f is 8. Plug in 8 here and graph 8 equals 2x minus 3y plus 5, but erase any part of that line that's outside the red, or only graph the part of that line that's inside the red. And do it again for f is 6 and f is 4. And so you could do this for all the different possible values of f and graph this and see what happens. See if you can graph these four and see what happens with that. Okay, so you're graphing 4 line segments, and these are the 4 line segments that you come up with. So if f equals 4, that puts a 4 here, and we graph 4 equals 2x minus 3y plus 5, and that is a line that's going right across here, but we only include it from this point on the boundary curve y equals 2x to this point on the boundary curve negative 4x plus 6. Okay, and it's only those in between. And then if we do it again for f is 6, we get graph 6 equals 2x minus 3y plus 5. We get this line right here, and we only get this part of the line, and this intersects the boundary curve here at x equals 0, and over here at intersects the curve y equals negative 4x plus 6. And similar, we can do it for f is 8 and f is 10. Well, what do you notice about these graphs? Well, first of all, what shape are they? Okay, they're line segments. And do you notice something else about them? They're actually parallel. If this is the graph of a plane up here, or in other words, a linear function in 2 variables, linear type function in 2 variables, then what we're going to always get is, graphically a graph of a plane there in 3 dimensions, but what we're going to get graphed here when we do this, when we specify specific values for f, we're going to get what we call a contour graph. That's in general, but if this is a graph of a plane or a linear function, these will be parallel lines. And going one direction, notice the lines get bigger in values of f, and the other way the lines get smaller in values of f. So what's it going to look like if we graph, without actually figuring it out, what do you think it's going to look like if we let f equals 2 or f equals 12? Yeah, notice how these lines are kind of evenly spaced? We're going to go the same amount of space up here and we get f equals 2, and the same amount of space down here we get f equals 12. Alright, now let's think about it a minute. If you go this direction, basically up from this line, you're going to be getting a smaller value of f. Okay? But anything along this line, all these inputs along this line have the same output value. That's f equals 4. So if you're at this point on the boundary curve, or this one on this boundary curve, or any of these points in between, you all get the same f value. Down here we get a different f value, but all the same along this line segment. F is 6 everywhere along this line segment, and so forth. But if we look, if we go, we can always get bigger than this line, bigger than this value, if we just go down some, right? Or go actually down and to the right a little bit. Okay, so where's it going to get the biggest? Well, it's going to get the biggest if we get these parallel lines the furthest down, and the furthest down one is going to go through this point right here at 0, negative 3. And so that means that's going to be the place where the function is its biggest. And where's the smallest? All the way at sort of the opposite end, up here. And sure enough, if you plug in x is 1 and y is 2 in this formula, you'll get an f value of 1, and down here we'll get an f value of 14 when we plug in x is 0 and y is -3. Okay, so if you kind of see what's going on here, if this is a linear function and your boundary is closed and bounded and it's straight line segments so that we have a polygon and its interior for the domain, all these are going to be line segments, and where's the biggest going to happen? Well, it's got to happen at one of the vertices. And where's the minimum? Going to be also at one of the vertices, probably the other side of the figure. Okay? So this leads us to linear programming applications. So in linear programming applications, the domain is restricted to a set of points in a plane satisfying a system of inequalities in two variables. These inequalities are called the constraints. And we want to find the minimum and maximum values that a function takes on, where the function is a function of two variables and it's defined on that domain. It's restricted to that domain only, the one we have graphed. Okay, so basically we have a polygon. Well, let's put it this way. If we do have a polygon and its interior points, closed boundary, interior points, but nothing outside of it for the domain, so line segments for the sides that are included, shade the middle part, it's closed, it's bounded, it's a polygon, and it's interior. That's the domain. And if the function is linear that we're maximizing and minimizing, then that has to occur at one of the vertices has to be the minimum value for the function, and another vertex has to be the maximum. Now, by the way, let me show you one thing that could possibly happen. What if this top curve, or let's say this bottom curve, what if this bottom curve was actually parallel to that? Then there would be one of these level curves, right, one of these contours that would hit, that would agree, it would be the same as this bottom line. And so that's going to happen if you ever get a table and you get the same value at two vertices that are adjacent, then it turns out that the whole line would be the same, and so it would reach, say, a maximum all the way along this line if what? If that line was actually parallel to these contours, if it actually was one of these contours. So if you got the same output at two vertices, then that's the same output all the way along that line. Okay? That's kind of an unusual situation for that to happen. So how are we going to do these? How are we going to solve these linear programming applications? Well, we graph the domain and find all the vertices. Okay. Then we must make us a big table of all those x's and y's, and then evaluate the function f at each of those x, y values, and then look at your f values. Whichever one of those is the biggest that the function can take on, and you know what x value gives you that. And similarly, whichever one of those f values is the smallest, that's the smallest the function can take on, and you also know the y value of that. So let's look at a couple of application problems, and you'll see that this has a lot of real-world applications here. So in this application, a farmer has 240 acres of cropland. The farmer wishes to plant corn and oats. His profit is $40 per acre for corn and $30 per acre of oats. Now, if that was all there was to the problem, then there's it's a pretty easy problem to solve about what's going to do the best for him. Well, it gets more profit per acre for corn. Just plant it all in corn. The problem is the corn requires more labor per acre to implement. So it requires 2 hours of labor per acre, and the oats requires 1 hour of labor per acre. Okay, and he only has 320 hours of labor available. Okay, he only has so many people he can hire, or so much work he can put into play here, and so he has a constraint there. So, given all these constraints, how many acres of each crop should he plant in order to maximize his profit? Okay, so here's a hint. Let's give. If we want to use our generic letters x and y, maybe we'll let corn, the number of acres of corn, be x, and say oats y, or you could do it the other way around. I did it x corn and y oats. Okay? And then write down all of the constraints. Write down all your inequalities that are going to give you the relationships, that the restrictions that we have on what x and y could possibly be based on the context of the problem. Once you get those, graph those inequalities, that system inequalities, reduce it down to a whatever region that you get, okay? And then you also want to write down a profit function, which is a function of x and y, and then maximize that. Okay? Try that yourself now. Press pause. Okay, so you're back. Now the first thing is identify the letters that we put in for variables. So we're going to let x be the acres of corn planted and y be the acres of oats planted. We have some physical constraints. First of all, x has to be greater than or equal to 0. We can't plant a negative number of acres of something. We could plant 0 in something. We could plant all corn perhaps, or all oats. And if it fits in our constraints, maybe we want to plant all corn, for example. But we've got to be positive or 0. So x is greater than or equal to 0, and so is y. Now, but the total acres is 240. We can't exceed that. So if we add x plus y, it has to be less than or equal to 240. So right there, that eliminates us down to a little bit. But then we also have another constraint, and that's our labor constraint. And that is we have 2 hours times x is the amount of labor in how many hours of labor for the corn, and 1 hour times y is the labor for oats. So 2x plus y is the labor for total, and that has to be less than or equal to 320 hours of labor. So that's a system of inequalities with 4 inequalities. X is greater than or equal to 0, y is greater than or equal to 0, x plus y is less than or equal to 240, and 2x plus y is less than or equal to 320. You'll want to graph that and find your solution set. I'll give you a hint. It's going to turn out to be a quadrilateral. And then we're going to maximize this profit function on that. We could also find the minimum, but of course the farmer doesn't want to be at the minimum. He wants to be at the maximum. Okay, so if you haven't gotten this finished, see if you can do it with this information. So press pause again, work this out, and come back. Alright, so here's our graph here on the right. Y equals 0 is a boundary curve. X equals 0 is another boundary curve. So x greater than or equal to 0 and y greater than or equal to 0, that already limits us to the first quadrant. And then we have our boundary curve x plus y equals 240, and our other boundary curve 2x plus y equals 320. Those two curves intersect at the point 80, 160. Notice there we're solving a linear system of equations to find that boundary point. And that's going to be a point that we need to find. And we can use whatever methods we want. We can use elimination, substitution, Gauss-Jordan elimination, whichever one you like. And if I give you one like this on a test, it's probably going to be with the calculator, so you can even use the Gauss-Jordan on the calculator, or you can use the intersection of graphs method on the calculator. So several different ways of doing it. In fact, maybe you want to do it just by calculating the intersection of the graphs, since you probably want to see the graphs anyway. So you might just graph these boundary curves on your calculator and then try to calculate this point of intersection, and then when you transfer it over to graph paper, you'll know where to put that. These points here are quite a bit easier to get. When x is equal to 0, we can see this one has y equals 240, so 0, 240 is easy to find. And this one down here is also pretty easy. When y is equal to 0, 2x is 320, so x is 160. And of course 0, 0 is the easiest to find of all. And it turns out that this region is the domain. So we can have anywhere on this border or anywhere in between here in the middle of this region is going to be allowable. But we know, since this is a closed, bounded, polygonal region, so it has a polygon here and its interior, and we know that this is a linear profit function, which is 40 times x plus 30 times y, is our profit, in dollars of course, that we know the maximum is going to happen at one of these vertices. And so we just write down all the vertices, 0, 0, 0, 240, 80, 160, and 160, 0, and then plug those in here, the x's and y's, to find my profit. And of course 0 is the minimum, which makes sense. If he doesn't plant any of it, he makes 0 profit, which is of course the least he could make. But the best thing he's going to do is right here is at 8,000, and that happens right here at this point at 80, 160. So the profit is maximized at $8,000 when 80 acres of corn and 160 acres of oats are planted. So given these restraints that he had, the best thing he can do is plant 80 acres of corn and 160 acres of oats, and that will give him his best profit. Okay, how about one more example here? An airline with two types of airplanes has contracted with the tour group to provide transportation for a minimum of 2,000 first-class passengers, 1,500 tourist class, and 2,400 economy class passengers. For a certain trip, the first type of plane can accommodate up to 40 first class, 40 tourist class, and 120 economy class passengers. And they have another type of plane that can accommodate 80 first class, 30 tourist, and 40 economy class. Now they can send a plane with some empty seats if they need to, but they want to do this as economically as they can. So they want to try to figure out how many of each type of plane that they need to send. Now, the first kind of plane, it costs $12,000 to fly it for the trip, and $10,000 for the second type of plane. So how many of each type of plane do they use to minimize the operating cost? So let's let X be the number of type 1 planes and Y be the number of type 2 planes that they use, and then write down your constraints, and then graph the region, find those corners, okay, those vertices, and then I think there's one more condition. Yeah, there's one more condition I want to give, and that is there's a limit on how many of each type of plane that they can have. I need to put that back in. I don't think I have it over here. Put it right here. Make this a little smaller so you can see it. And then go back. There we go. So there's one more condition here. They don't have unlimited planes. They only have 60 of the type 1 plane. They can only do 60 flights. Either they only have 60 planes, or they can do them multiple times, but they can only make that many flights because they're limited to how many they can send. And they can only do 80 flights of the type 2 plane. Okay, so there's another couple conditions there. So with those conditions, make your system of equations, graph the feasible region, the domain, okay, find the corners of that polygon, if it is a polygon. If it's unbounded, then we don't know for sure if there would be a maximum or a minimum, but we can investigate and maybe find out. Okay, and then evaluate at each of those vertices and see what happens. And again, if it's bounded and closed, then the maximum and minimum will happen on one of those vertices. If it's unbounded, then we have to see maybe there is no maximum or minimum depending on which way we go with it. Okay, so see if you can work this out now. Okay, here it is all worked out. X is the number of type 1 planes, Y is the number of type 2 planes. Well, X has to be between 0 and 60. So that gives you a vertical line here at X equals 0 and another vertical line at X equals 60. And we have to be between those two lines. And similarly, Y has between 0 and 80. So it's between the horizontal lines here at the x-axis and up here at 80. So we're within that rectangle to start with. So nothing outside that rectangle even makes sense, and some of it inside doesn't make sense either. Now look at the first class here. How many first-class passengers? Well, if we have X planes of type 1 and they do 40 each, that's 40X. But we also have Y planes of type 2 and they have 80 first class, so that's 40X plus 80Y. And we have to have at least 2,000. Okay, we could have extra seats and fly a few empties, that's okay, but we can't fly less than 2,000 because we got to accommodate all these passengers that they've got. So that's 40X plus 80Y is greater than or equal to 2,000. That gives us this line down kind of down here, and we get above that. So that erases a little triangular bit down here out of our rectangle. Now the tourist class, similarly, the first plane has 40 of those, and then 30 for the other plane, so that's 40X plus 30Y, and we got to have at least 1,500 of those altogether. So 40X plus 30Y is greater or equal to 1,500. That's this sort of line segment here, and that would erase another bit off of this. And then finally we erase this little bit here because the economy class we have 120X plus 40Y is greater than or equal to 2,400, and so that erases a bit here. And the only thing left is this part here, which is shaded 1, 2, 3, 4, 5, 6, 7. There's 7 things. 1, 2, 3, 4, 5, 6, 7 equations there. 1, 2, 3, 4, 5, 6. And there's a 7-sided polygon here. Okay? Now, well, that gives us 7 vertices. Oops, 1, 2, 3, 4, 5, 6. Oh, I'm missing one. 50, 0. Let's see. 50, 0, 60, 0, 60, 80, 0, 80, 0, 60, 642. And 642 could be the best answer. I need to go back and edit this to see if that's the best answer. So I need to add another line to my table. 642. Let's see here. So let me check that out. 6 and 42. And I need to work this out. Okay, we need 10,000 times so we need 6 times the 10,000 plus 42 times the 12,000, and that is 564,000. So it's not our least, but it's a good thing we check that. Okay, so the one that was the least actually is not that one. It's actually this one right here. It's the one on the bottom there at 420,000. Okay, so that is the least amount. Okay, and so that's it. Now the worst case they could do is do 60 of the first plane and 80 of the second plane. That's right out here, so that would be the worst. In fact, the further they get out here away from the origin, the worst case scenario it is. Okay, so there's the worst case scenario there. The best case was this one right here at 30 of type 1 plane and 10 of type 2 planes. Okay, that occurs right there, and it's going to cost them 420,000 when we do that. So, what should you be able to do? Understand the difference. I didn't finish this. This is still from another thing. Okay, this should be now for These goals should be for systems of linear inequalities. Okay, and you should be able to graph the solution set to a system of linear inequalities and you should be able to solve linear programming applications. Okay, and that will take care of us for this particular video.